Okay, so just a brief recap of the Flare on Challenge. I suppose you guys already know it pretty well. It's one of the most prestigious reverse engineering challenge in the world, and this year they have 9 challenges. I think it's pretty much the smallest one. I'm not sure, at least in recent years. And also, it only ran for 4 weeks. The winners get a bag. I'm expecting mine, but I'm not sure whether how soon or late it will come. I think I will just wear this to DEF CON next year. And for whoever also has this, please also wear it so that we can recognize each other. Um, is it better? All good? Cool. All right. All right. So let's get started. So I'm going to talk about the challenge 7, the boss needs help, which is made by one of my friend Maurice. And also, I think it's the most flare on challenge is like I mean in the sense that it actually fits into the the feeling of flare on. It's also a very interesting showcase for TTD. So we were given two things. One is the executable Hope and Dreams.exe. Oh, big name. I didn't realize that. I just thought it's like something dreams. I didn't read it. And also given a package dot capture. So if you see the contents, it will be pretty much all encrypted because you can see here this is surely something encrypted, and it just goes on and goes on and goes on. So I think it's pretty clear that the task is to just analyze it and decrypt this traffic and then be able to solve it. So the first thing I did is I loaded the challenge in Ninja, and before we get into TDD, there is something we can realize, we can notice already is basically this main function is huge. You can see here, you probably won't be able to read it. Like even if you just switch to the high level IO, it's still very confusing to read. Now this challenge is also heavily obfuscated if you already read the write-ups. Interestingly, during the time of the challenge, I didn't actually work out a full deobfuscation, but I did actually make it a little bit more readable. So you can see here, is the font large enough? Cool. Okay. So you can see here at this instruction is loading this constant and it does some calculation on it, and then it loads and eventually writes the value here. Now, in many of the samples I have seen before, usually this is actually a constant value. And this whole thing, I mean, this 5 instruction sequence actually just writes a constant value into the var underscore 438. Now, but this case is kind of special because as I noticed, there are actually a lot of writes to it. So um, you can see here, even in the first function, there is already a write to it, and the value gets written to it is not really obvious what it is. And as we move on, there are you can see altogether 894 references to it, and a good amount of them is actually writing to it. So initially, I was a little bit confused because for most of the malware or obfuscated samples I have seen, basically it should just have a constant value, and you basically just set the type of it to a constant, and uh, then our uh, Dataflow engine will be able to solve it. But this sample I use for one moment because I see that there are also writes to it and the values actually vary. And I wasn't very sure what is happening because if it can take a different value every time, how should I even try to set a constant value to it? But then after I dig into the code further, I realized, so these are actually just junk code because you can see here, uh, these values are really never used in a useful way. And at the end of it, you can actually see there are also assignments to it. So basically, what this particular obfuscation does is just is writing and is reading its value, does some calculation, and write it back, so that the compiler wouldn't actually just go ahead and remove it, defeating the whole purpose of the obfuscation. But the actual value of these global data variable is useless to the actual algorithm or whatever the original user code. So realizing this, I find out that we can still just set it to constant. And after we do this, you can see this the oh, it, let me just do it one by one. I mean, this can be automated, but for just 5 of them, I'm not going to bother with that. Okay, so let's get back to the main function. And so, and it's already surprisingly much more readable compared to the original. But it's also obvious to realize that it doesn't actually remove all of the obfuscation. So for example, our data flow engine does have certain cases where we do not handle. It's like Moz dot double precision dot double word. So this actually can be calculated because it's just like dividing one constant value with another. But we just haven't handled it yet. And also there are situations where uh, these things just add up, and eventually this branch also does not get simplified because some of the values previously was not properly determined. Uh, as a result, it doesn't actually get fully simplified. But this is already much more simpler than what we saw previously. So during the game, during the time of the challenge, I tried to actually come up with a full deobfuscation or something, but I feel like it's not worth it. So I went directly to the TTD solution and used dynamic analysis. So after the event is over, I do see other people sharing write-ups on how to actually use our API to uh, do a full deobfuscation. And I also encourage you guys to check it out because the idea is pretty simple. We know that we know that 5 things, uh, these things are users. So you can either tint forward. So basically everything gets tinted by this data variable is user, so you can patch it. Or you can start from the end of the main function. Basically everything is still tint based. So uh, okay, see here, we have this right? Uh, why it doesn't sync? Okay, so we have this right, and we can track its value, and everything that actually contributes to it is all just our distraction. So you can actually write a pretty simple tint analysis based deobfuscation script and remove all of the deobfuscation and have a clean binary. I mean, if we get a chance later, I'm not in this stream, but maybe later, we can actually also explore it. But today I'm going to stay focused on TTD and not really trying to do that. But it's still a thing that is interesting to try. All right, so yeah, let me get into TTD. Uh, I remember the first thing I tried was to just run this binary, and it just exits. And the way I did a TDD recording is so first of all, if you haven't really done any TDD before, like this is your first time being exposed to TDD in Binary Ninja, you'd have to run this install WinDbg slash TDD, and it will just download WinDbg and install WinDbg TDD onto your machine into a place that Binary Ninja is accessible. So you can also install WinDbg outside of Binary Ninja, but that doesn't actually help us because we have to install it into a position we know and we can actually load the DLLs from so that you can leverage it. So if you haven't done this before, you just do install WinDbg slash TDD and it will just be automatically downloading from Microsoft server and put it somewhere we can access. It might take a few minutes, but usually it should just work. And then once you have that, you can click, then you have to restart Binary Ninja to load the new DLLs and then do debugger record TTD trace. And then you can select the executable path, working directory, and command line arguments. I'm leaving all of these as is default because it works for me. And or maybe I can put it in a new folder to just show this to you. Okay. So this is the trace output directory. I just want to show how to actually do a recording. And the UEC dialog will show up. I'm not sure whether you guys can see this because of formation issues. But the UAC dialog will show up and ask you to confirm the recording, and you just click yes, and it will be executed and recorded. So you can see the tracing has already been finished. It's pretty fast. It took a few seconds, and also the trace size is like 40 megabytes. Like in my opinion, given the modern day disk size, this is actually pretty small. And the ROM file is the thing that we're going to be loading with. All right. So the next thing is we do is to load the trace. So I'm going to load the old trace I used during the CTF. I'm not really using the new trace because uh, I already have some configs that will interfere with it. So the first thing you want to do is you want to switch to debug engine underscore TTD. Now, this drop-down selection is pretty new. I mean, I think I checked it in last week. So unless you're using the latest style builds, like me, uh, you will have to maybe select it from here. You just click this wheel button and it will show up and you can select debug engine underscore TTD and then it's pretty much the same, but I will just do it here. I cut out the sound or the video.
You're both, but you're back now.
I'm sorry about that. Do you want to talk a little bit? Like, take it from me briefly?
Yeah, sorry, I've been just managing things behind the hood here that's been going wrong on stream, just balancing audio levels and stuff. Um, but did you define taint analysis for us? We often take the definition of that for granted. But I'd love to see. Well, you're talking about doing it over data variables, and I'd just like to continue seeing that demo. Because
Pardon?
we don't really have a lot of taint analysis features built into Binja, but taint analysis is a cool thing to be able to do. Just something
Yeah.
you were talking about a little bit earlier.
Yeah, I think I mean we can totally explore that approach later, or maybe in another stream if that is the interest. This challenge is actually having pretty cool depth in terms of the obfuscation and the overall algorithm thing. So it's pretty cool challenge. I mean, I don't mind if we actually invest a little bit more time to show people how to do things in a more binary ninja way because that is uh, just helping people learning the tool better. All right,
Right.
so let's get back to the topic, and I will be loading the trace.
So at
So
this
I select.
point, you've run the program, you've traced the program, you've loaded the run file, and now we can start our time travel session, right?
Oh, yes, I'm about to be able to load the trace. So what you do it is basically you first of all ensure the debug adapter is selected debug engine underscore TTD. Now this is one of the most common mistake people forget to do, and they will just try use the debug engine, but then you selected a trace and if you do not select the correct debug adapter, it will try to execute this trace file as if it's an exe, which of course wouldn't work, right? Because this is not an exe. So just remember to select the debug adapter in the dropdown to select debug engine underscore TTD and then click accept. So this is the first time the trace being loaded. Uh, you can see, yeah, the view is being rebased pretty fast. So, oh, yeah, this is already not the first time this trace has been loaded because I have already loaded it multiple times when I well, during the CTF. So you can see here it says indexed 5 out of 5 keyframes. If you load a trace for the very, very first time, it will spend some time indexing the trace, making it faster to access afterwards, which also means potentially the first load can be slower, but that is all totally worth it because one, it doesn't actually take very long. It says 514 milliseconds, which is pretty negligible. And also, it ensures the subsequent queries can be much, much faster. All right, so uh, I do have so this has been like so today is October 31, and I think I did it at the start of October. And between that day from today, I actually also shipped some new features on the TTD, which I'm also happy to share. It's like TTD events.
Yeah, I
So
was
this is
looking
a
at this in the feature stream, and I know that you were talking about adding all sorts of different events in here potentially. So I'm cool to see what you've been curious to see what you've been working on.
yeah. So this is a TTD event that was previously not available, and it's even not available to me because I was just haven't get to there yet. So you can see here it shows all of DLLs that has been loaded. And of course, it starts with the hopeanddreams.exe, which is the main module. It also loads the TTD record.cpu.dll, which is essential for the recording, and it also has all of the other DLLs that has been loaded. And particularly interesting is a WS2 underscore 32.dll, which is essential for Windows networking. So we will also be querying calls into that because we want to understand how the things work out. And also, you can actually double click on any of these positions and time travel to that. Because, for example, if I select F:0 and double click on it, I will just be time traveling to the exact moment where this DLL is loaded. And also we have all of the threads. You can see here 3 threads has been created, and this is the main thread, of course. Uh, I guess one of them can be the networking thread if that is the case, because it starts pretty late. It's like 999 180D into that. I don't know how to read it, ATD or something. Sounds very weird. But anyways, yeah.
What are those timestamps actually coming from? Why are they written like that?
Oh, so that's just a way to make it more recognizable. Basically, it's just two numbers, like a sequence and an index. They just decided that they will write it in a sequence colon step way so that is uh, more easily readable. I'm actually not sure what it actually means, but you just feel like when the step goes from 0 to all the way to hex FFF, the sequence will be incremented by 1.
All right,
So yeah,
interesting. Sure, why not?
sequence, yeah, yeah. So we also have exceptions. We don't have exceptions. Cool. Yeah. All right. So this is the very first time I run it, and as I mentioned, when I run it, it actually just does nothing and exits. So the first thing I remember I did is basically I want to see all of the networking things that has been done, and I will limit the calls to be made from the main module. This is basically this query will basically say I want to query all of the calls into any function into WS2 underscore 32, but also requiring that the call has to be made from the main module, which is the user code is from. All right, so I will just run the query. It's executing the query. Yeah, it might take a little bit long because, well, it already finished before I can finish. So it's not really so long. But anyways, so uh, you can see here we have 10 calls into the WS2 underscore 32 function DLL. And the first one is always the same, it's WSE startup. If you're familiar with how sockets work on Windows, you will surely know what's happening here. And here is the most important thing we care about is calling get address info. Basically, that is trying to resolve a DNS. So now, this challenge binary is connecting to a domain that is fictional or something doesn't exist in the real world because it's a fictional story. So it surely is doing some DNS resolving. And we can see here, uh, yeah, let me pull up the, what is it called? Get address info. Okay, cool. Yeah. Yeah, you can just look up the function prototype of it, and you will see the first one, the first parameter in RCX is the is the domain name that is being resolved. And of course, we already see it here is 12.flareon.com. So this is the domain name is trying to connect to. And this domain name, uh, I'm pretty sure it's fictional and it doesn't exist. So I have to edit my host name to point it uh, to localhost so that it actually works. So this is basically Windows System Standard 32. Uh, where is the Windows host file? Okay, it's here. All right. So this is my host file. Again, so I'm not really trying to show it step by step. So the host is already here. Um, I basically just redirected to my local host and also just spawn up a server that returns something random. So if we look at the original, the first packet or the first conversation in the trace, you can see here is it sends a request to 12.flareon.com colon 8000. Now, of course, you can see you can also find out the domain name from here. You don't have to do the TTD thing and figure it out. Right, you can totally do that. I'm just showing how I approach this because I just didn't realize it's already in this file. I just went ahead and deduced it from here. The RCX is domain name, the RDX is the port. And also, so what I see here is it sends a D in a JSON response. This is pretty much encrypted. So one of the target of ours is to actually decrypt this. At this time, I actually noticed the authorization colon bearer, and it's also a hexadecimal value. But at the time, I just think this is some random thing because I was thinking maybe the bearer is just randomly generated, and the server has to respond to it properly. So maybe it's kind of like this D is either a encrypted version of something of the bearer or something. So basically, the server has to authenticate itself to the client because the client is pretty much like a RAD, it's a remote access tooling, and that it won't actually listen to anything it gets. You have to first authenticate yourself to be able to be trusted by that. So although later on I learned the bearer is actually not random, but at this moment I was thinking the bearer is random, and my script actually just returned the very same D value I see from the packet. Uh, and I run it again, and what I observe is, so now that I have the DNS config and I have my Python script listening on the host, and my script is returning the data that I see in the Wireshark. But after that, I'm not seeing anything from the client anymore. Like in this packet capture, the client actually goes on to request a pretty long domain name, the annual whatever, and also continue the conversation. But in my case, when I send the exact same response back, the client just exits and refuses to talk to me. So then I realized maybe um, even so I realized the response I sent is not making the client happy. So the client refuses to talk me further. And in this case, what I was doing is basically I want to put a breakpoint or use TTD to actually find how is the packet received, and then trace it to the logic where this gets decrypted and the data revealed. So what I did is basically I did another recording after I had the server set up, and it actually receives this packet, and I believe it internally decrypts it. So what I'm going to do here is I will load up this trace and start it. Are you guys able to follow my logic, or do I do a good job in explaining what I'm thinking? Because I do realize it's a little bit complicated to try to explain this in a unscripted
Chat
way.
seems to be following along. People are saying that this is a pretty cool feature. We've got a feature request, and Jordan already filed an issue for us during stream, it looks like. So I think you're doing a good job.
Yeah, sure. So we all know we need to put a breakpoint on the receive. Yeah, this is a little bit challenging to do it in an unscripted way because I just have to remember how I did it. So the receive function in winsock.h is the one that will be actually receiving the JSON data my Python server returned, and we need to figure out is also in WS32. This time I will just query specifically for the receive function. And also again, I am putting the address range of the executable of the challenge because I don't want to, because any of these DLLs can actually also make a call to receive, but that is almost certainly not what I want. So I kind of just want to limit the address range to the module I'm interested in, and I will just do the query. Okay, we found three of them, which means it actually receives three buffers from the remote. I actually do not remember which one it is, so we can actually just see them one by one. So you can also see the second parameter is the thing that receives the buffer. So we can actually create stack view and also okay put it here and also navigate. So this is the time of the start. It's before the function. It's before the call is made. So we can actually navigate to RDX at this moment, and then either we just step return and let the function finish, and you can see it receives the HTTP header, or we can also directly just double click the time end, and it will also just navigate to the time end, and it will show the same thing, right? We can do the same thing for the second time step as well, and also remember to navigate to RDX, and then we can do a step return and see whether that is what I want. Okay, we already see this is what I want. You guys see this? So this is already the JSON that I returned, and this JSON does not make the client happy because after receiving this, maybe it does some internal processing and eventually it just exits. So what we are going to do here is, so like even if you don't have a lot of programming skills, you will know that what happens with this buffer is it will go through a JSON parsing library, and also it will be copied. So the JSON parsing library will basically say, oh, okay, this is a JSON, and it's having a field called D, and it's going to, extract this part of the string and put it elsewhere, which can be used. So this buffer will be copied a few times before it actually goes into the processing. Let's say call it decryption. So this buffer will also probably first be now this is hex, right? So it will be also converted from hex to uh, the raw bytes and then goes through the decryption. So what I'm trying to see here is basically this buffer will be copied a few times before it actually get used. So I can also show this. So what I'm going to do here is I will select the first byte and right click and debugger memory access read. So I want to see when this buffer gets read next time. And okay, yeah, we have a new widget. It's called TDD memory. And what it does is basically it shows all of the memory reads to this location. And of course,
We have a
it shows
question. Someone's asking if the decryption routine will happen on the server side.
no, the decryption also have the decryption happens on the client side. The client is the executable we have because after I send this packet to it, it actually processes it and decrypt it and does validation on it. And because I don't know what's encrypted in it, the thing I return is not making it happy, so it just exits. And what we are trying to do here is trying to trace it and see how and basically trace it to the point where it actually gets decrypted and understand how the decryption is done. Yeah, cool. All right, so we will see we see 16 memory access events. So how do we know which one we want to know? So first of all, we can see the contents here. We can see the value that actually gets read, right? Only in the last one, the value being read is correct, right? It's 32, 64, 61, 36, and also it's 32, 64, 61, 36, right? And also if you press Shift G, you can see that current time step is 9E2:40. Now we are looking at any reads to it after that because we're at 9E2:40, and 9E2:40 is the time that we receive this particular buffer from the socket. And anything interesting to us can only happen after that. And we can also see there is only one time step that is after that is 92:479, right? So this one is actually the one we are interested in. And
We
I
have
will just double click.
we have another question here. Someone was asking. I believe that this is working for the entire range of bytes, so you don't have to select the first byte of the string to see the memory insights for them. You can select any of the bytes, and it's tracking all the reads and writes.
Not exactly. So the
No,
buffer
okay.
is here. And the reason I skipped some of the bytes is now this is actually a technique, but I'm not really trying to argue that is the optimal one, but I can
Mm,
explain my logic here. Now, of course, you wouldn't want to select any of these bytes, right? Because that is where the JSON is still parsing the structure. We are only interested in where this particular encrypted the value is used. So you have to select something that is in this part of the selection. You don't want to select the colon. You don't want to select the code. You don't want to select the parenthesis. And also the reason I selected something that is on a aligned address is because well this is pretty subtle. So selecting a aligned address can usually sometimes gets you to a start of a loop. So
mm,
you know this is getting into CPU architecture. And in
mm-hmm.
this particular case, it actually doesn't matter because you select anything, it actually just works. But for example, if it actually does it in a loop and is processing it byte by byte, you might actually get into the start of a certain part of a loop if it's actually trying to leverage the aligned nature of the buffer.
Yeah, that makes
So
sense. That's really
uh,
clever.
yeah, so and also you know another consideration here is what if it actually maybe the first 2 bytes is the length and the rest of this is the content? Again, of course, in this particular case, that is not the case, but it could be happen that maybe the first byte is processed in a different way. So I just want to select in the middle of that so that I can, without knowing what actually happens, I have a best chance of actually getting to where I am interested in. Again, of course, in this particular challenge, in this particular place, it doesn't really matter where you try to see the, you know, the access. But this is just kind of like what I'm used to do. Yeah, well, this is actually a perfect question. Thanks for bringing this up, and then I'm able to share some part of my internal thought process, which is otherwise probably I will just miss. Thank you. So, all right, so we have the time start, and I will just double click it to time travel to it, and you can see it's running, and it runs for like maybe 4 or 5 seconds. That is also very normal in TDD because TDD has to actually go, seek all of these uh, traces and to the correct place to um, give you the information you wanted. And also, I'm doing this on my laptop, which is not super performant. I was traveling when I did the challenge, so I don't have my regular PC on with me. But even this computer only has 32 gigs of RAM, and it's not super performant. I was able to actually just do it pretty well, which means also TDD can be helpful for you. So we are inside of a VC runtime DLL, and we're in memcopy AVX blah 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 somewhere. This is totally normal. Why? Because as I said, we will we will see this buffer copied a few times before it actually gets used, right? The JSON parsing library has to process it, and also maybe some other uh, you know, whatever things has to process it before it can be used. Now, for this kind of things, we don't actually really care uh, the details because it's just a mem copy, right? So we're just going to trace where it gets copied to. So we're inside of a mem copy function. I will just let it return, and the moment we let it return, we are after a mem copy call, and you can see we're actually inside of the user code, is inside of Hope and Dreams. The next thing I'm going to do is I will do a reverse. Okay, I don't have a wide enough screen. I do actually have a wide enough screen, but for the streaming purposes, I just cut it to 16 versus 9 to make it more readable. I will just do a reverse step over to go to the moment before the mem copy was done. Now you can see what's happening is basically RCX is the target buffer, RDX is the source. So it's basically copying this buffer into a different location, and we can see what is inside of RCX, and we just step over it. Okay, so you can see here, basically now the buffer is copied into this new location. And
I just want to say this is beyond cool. So, just to make sure that I know where we are and to recap for anyone who might be joining us, we started with the output we were seeing from the binary, and we were trying to make our own sort of emulating that interaction. But there was a bug, so we found a receive call, and we used the calls sidebar to see all the calls to that, to see all the data that was going through that receive call. And now we followed that buffer to this memcopy, which is moving it around as well.
yeah, all right.
All right.
So not surprisingly, what I'm going to do is to basically repeat the same process on the new buffer because that is where it is going to be used next. And we do see a lot of ones, but again, we can see the time step is 9E2 4B9, which is still pretty much the last one of it actually makes sense, right? Because the last one is larger than 9E2, D1 is smaller than E1, right? So that is actually before the last item is actually accessing this address, but after this particular time point, and we're just going to repeat the process again, I guess. All right, so I just did it, and we are no longer inside of a memcopy function. We are inside of somewhere hope and dreams. And if you see this function, uh, Yeah, okay. So this function is actually a JSON parsing library. How would I tell? Well, of course, you see invalid string control sequence blah blah blah, and also invalid string control sequence blah blah blah. Okay, lots of lots of invalid string, but I mean, you can just tell this is actually the JSON parsing library because, as I said, this buffer has to be processed before it can be used, and we are inside of a how should I say a user some user code. It's not library code. So this is 99% the JSON library. And what we're going to do here is we will just let the JSON library finish its parsing, and whenever it gets to only this part, we will continue to trace it, and then we can see where it gets used. So we can see REX is holding the buffer 3B2. Okay. It does increase. So this function is just making, yeah, sorry, I actually can't remember how I did it. Let me just try to explore it on the stream. It actually raised a byte from REX. REX is our buffer, so it's into the RCX, and RCX is written into R12. Let's just go to R12. R12, what is R12 holding? Let me create another stack view. Oh, it does, no. Yeah, okay, cool. So another cool skill I want to show here, if you want to navigate to the buffer at R12, you can use the $ followed by R12. Just use R12 as a value in your navigation. You can even add a value to it after that. So you don't have to really copy R12 here and just do it. You can do it there.
You just need the dollar
Yeah,
sign for
dollar
that?
sign.
Cool.
Yeah, yeah. That's one of the feature I really, really like. And people do not know about it,
I
which
didn't
made
know
me
about
kind
that.
of
No, that's
sad.
really nice, actually.
Yeah, yeah. So I think what happens is right to R12. Where is R12? Okay, R12 is here. It writes it. Yeah, it
There's a
writes one
question
byte
here.
here.
Did the JSON processing error strings exist originally in the binary, or did this code get unpacked after execution started? I believe they are in the binary, right?
I think it's in the binary. This binary is not otherwise obfuscated except for the thing we discussed earlier. It doesn't use packing, it doesn't do crazy things, it doesn't actually make it more challenging. I know all this kind of stuff can be combined to make it a terrible experience for the reverse engineer, but luckily, they didn't do that. R12, it moves here and then okay. I actually can't remember what I did next. So there are a couple of ways to do it. So we do have a thread here. We do have a bytes that is written to here, and we can trace on the read on it, and we can see what is the next moment that this is read. It's 9EE 9E0 9E 9E0. There is a lot of this. 9E0. What is the first one after?
Right now, are you just trying to find
Just go ahead.
all the other times that this data has was used in the program? Was read?
Pardon?
Right now, are you trying to find all the other times that this data was read?
Yes. So no, we're inside of the JSON parsing library. I remember what I did is actually I went through a few stack frames and see after a particular function call, it actually the string is already there.
Right.
But I just want to see take a more systematic approach and see if it works. If it doesn't work, it doesn't matter. I mean, I can still show you how I probably have did it during the event, but I'm just trying to explore something different
Yeah, go for it.
right now. Yeah, I mean, it's a little bit risky. Like if I fail, it could be a little bit awkward because people are all trying to see how TDD works and it doesn't work. But it
No, no,
doesn't
you're
matter. I
showing
mean,
us how it works. It's really interesting to be able to see all the different times in a program that bytes were read.
yeah,
Just to see, all the different places it's being
yeah.
used. You're showing off how time travel works in general.
Yeah, and of course I have to explain this stream is not scripted at all. It's like I finished Flare and I never come back to it. And this morning I just opened the trace and try to do it, and uh, yeah, it's just I don't know if
You know,
it's
it's
really
really
going to
cool
be.
because again, we're used to thinking about navigating through binaries like we normally do through, I guess, space. But being able to navigate through both where you are in the binary and when you are in the code, seeing multiple values in the same register or in data
Yeah.
is really, really cool. Really, really powerful.
Yeah, so it actually loads the value 32, 33 hex 32 from R15 and into REX. And it's as one to REX, and it compares with a. So this is typically still inside of the JSON parsing library, and we just need to track where it goes to eventually. So the REX has the value, I believe.
Yeah, makes sense.
CMP
We have
is going to
another
be.
question in chat. How are you tracking those memory events?
This is just from the TTD backend, so it's from the query of the Windbug.
So is that
Let me
going to
show you.
be moving like register to register? Is that only going to be when you're dereferencing addresses and stuff like that?
So out of the box, it only has the tracking between the memory addresses, so you can't really just ask where does this register change. But in the most recent version of Windbug, they actually added that, but that is very expensive. So basically, if you want to ask when does this ECX value change, it basically has to rewind every instruction and one by one, and it's basically ON in complexity, and it's
Right.
the number of instructions, right? But the memory access is basically they have efficient recording. They have an efficient data structure. So querying on memory addresses is pretty fast. So not well. Now that we are into this, so when a register change is combined with memory change, you essentially have a 10 tracking, either forward or backward. So turn tracking is one of the things that is, I think, is on the crown of TTD, which is the kind of like the most precious thing you can get from TTD, among other things as well. But turn tracking is one of the things that is on my radar
Right.
for a while, and eventually, I guess we will have a something, for it.
So
Uh,
then okay, so like the line right under the instruction you're on currently, that would trigger a memory event, right?
yes,
Okay.
yeah. So it's actually using RCX in a way that it's indexing. Oh, okay. I see what is happening. Okay, cool. Yeah, yeah, okay. Let's. I do see what's happening, but I just kind of this is actually Unicode parsing. So it's actually parsing the incoming value 3 as a char, but this JSON library is probably Unicode aware. So it's not only doing ASCII parsing, it also does Unicode parsing. I guess we can still potentially uh, figure it out. Let me just try a few and see if it works. If it doesn't, I can just always switch back to the safer approach. Uh, I do see a new question asking about a full string. So at this moment, it cannot be done because we don't have that information. These are all discrete. Um, but what I do plan to build is basically we already have all of the memory read and writes, right? And we can actually scan it. For example, like uh, we can just scan, okay, we see the first string is 0, the second char is 8, the third char is 5, the next char is D. And this looks like an ASCII string, right? And if that happens, we can just maybe record the longest ASCII string we see and potentially provide it as a list of string. Now, this list of string is super powerful. It's totally different from the static string scan on a binary because the string can maybe exist in RAM only briefly, right? And either in static analysis or traditional debugging, you would normally just miss it because it existed on the heap for a while and then gets discarded and it leaves no trace behind. But with TTD, with a scanning over the entire memory read and write and a efficient algorithm, you can potentially actually get the full list of not only strings. We do malware, you can potentially even get any of the buffers, and the buffer can be a PE, can be a configuration, can be anything, right? So this is where I think TTD is powerful. It's basically we have these what I'm using here is TTD memory and TTD calls. And of course, I will say it's already very cool. It's very powerful. But this is just more like the primitives of TTD access. So we have these from the trace. And with the help of this, we can actually build even more powerful analysis on top of it. So for example, like we know malware tends to do unpacking, right? And we can actually somehow query any of the instructions that has been written to before it actually gets executed. Now that single query will already give us the list of instructions that has been modified before execution. And what we need to do is basically find the first of such instruction and do a dump from the moment because that is where the unpacked code starts execution, right? So this is of course it will have some engineering challenges, make it more performant, more reliable, and stuff like that. But this is just a pretty cool idea of how TTD can fundamentally transform the how we do reverse engineering.
Yeah,
All
that's
right, so
really
back to the
interesting.
top.
Being able to search
Yeah.
for strings or values across the entire lifetime of the program would be helpful. Like being able to search for certain values you're finding in the program. Like I know in Cheat Engine, you can scan all of RAM for a certain value, like buy or sell something to change your money value, and then scan memory for that new value, and then you just find all locations that had the old value when you searched for it the first time, and now also have the new value to help you find
Yep.
things in the binary. So to be able to do something similar on a static trace in TDD here would be just awesome.
Yeah. Cool. All right. So I just gave this function a name JSON parsing, and I will just let it return from it because I'm not going to fight it with it more. And I just want to proceed with the demonstration and not to try to waste too much time on it. So I will just return from this function. And cool, we are inside of another function. If I remember correctly, so based on my memory, this is still inside of the. Okay, cool. What it is? Oh yeah, you can still see here the keyword value, stuff like that. That is indicating we're still inside of part of the JSON parsing library. And of course, so a typical way of dealing with this is to actually try to have a type library, signature library to match the function, and it will give you the function names on this. But I didn't do this during the challenge, and I also don't feel like I'm doing it right now. And of course, but I just want to mention we do have warp uh, to help with the situation. And of course, we also used warp today to show how TDD is powerful, but that is the different warp. Warp is our signature matching solution. It potentially can also solve this problem in an elegant way. I will just see so I will just go back a little bit, take a step over backwards and see what is on the on in the parameters. RCX is having what? RCX has okay.
We got the comment that we forgot what we're doing. The people following along might not be following along. So right now we're trying to find where this buffer is being processed, I believe, right?
Yes. We're trying to wiggle out of this annoying JSON parsing library and see where the string gets out of JSON parsing and gets into the real processing. And
Yeah.
we're still inside of a JSON parsing library, so I can comfortably just let it return.
We were able to find the data coming from the network. Then we saw the data get copied around in the binary a little bit. Now we're seeing it being parsed as JSON, and we're just trying to find the result of that parsing.
Yeah. So let me try to do this. So you can see here, I am not sure whether this function is still part of JSON or is still part of the user code already. I think it's still part of JSON.
Is there a reason that you tend to be looking at the disassembly rather than the decompilation?
So, oh yes. So, no, it just happens to be at the disassembly.
Okay.
Oh, I thought you were asking why I still believe this is inside of JSON parsing library. So first of all, the call stack is still very deep,
Mm-hmm.
and we can see we still see things like value and a few different keywords that
Yeah,
is
there's
indicating.
exceptions in there as well.
Yeah, so this is not totally scientific. I'm just trusting my instinct on this, and
It is possible that those are just errors that got inlined where we're querying for values, but I agree with you. I think this is probably also still one level too far down. That looks a little bit better to me.
yeah. Let me try to restart step. So what I typically do in this situation is I will just try
Oh,
to
I see. Yeah. Okay, so you're exiting those function calls we're finding, and then you're stepping backwards to see what the parameters were to them before it executed
yes,
to figure out what the function's
yeah,
doing. That's so cool.
yeah. This is also another thing you can't actually do in traditional debugging.
Yeah,
RCX
just being able
RDX.
to like literally switch between the outputs and the inputs. That's really awesome.
Yeah. Okay. Let me. Oh, it doesn't work. Yeah, maybe I should have prepared this a little bit beforehand.
Oh no,
Try
no, this
to
is
make.
good. Don't worry about it. This is what the people want to see: how to use Binja, how to reverse, how to when you fall into these traps, how to get yourself out of them. And we are having some aha moments, so it's all good.
Yeah, this is super weird. I don't, I can't. Let me. Okay, let's shit it a little bit. Let's go to my
Ah, here we go. Okay. I don't think anyone minds
uh
if you look at your notes.
let's go to the notes here.
So there's a question: does anything like TTT exist for Linux or QEMU?
Yes. So so on Linux we have RR from Mozilla, and also we have Ondu from a different company, and also we always have the solution ES reverse or ES driven, which is based on QEMU and basically supports anything that runs inside of QEMU, including Windows, Linux, and also some of the phones. Yeah, ES reverse is also something that I'm working on integrating with, and also that is where I think we have a demo coming up in maybe October, or, sorry, December or something. Basically, I will
Yeah.
also demonstrating some of the TDD integrations with ES reverse. Yeah, yeah. There is also Panda. Yeah, cool. Okay, cool. Let me. Yeah, let me try to just focus on this a little bit and try to figure it out
Yeah, think
what
it through.
what goes next. Yeah, maybe Kyle can take the talk from me if you feel
Yeah, no, sure. Just
okay.
tried to think about what to talk about here. I'm just still enamored over the fact that we can look at some bytes and see everywhere in the program they're being read. It's making me think of like what would we want cross references to look like in a world where we have both the code reference and data references, but also like time references. And if we could build out a graph where we show literally the different places that are reading and writing different addresses at different times, and if like that sort of visualization could help us explore the data flow better. Um, and I'm sure we have all the APIs to be able to query when values are being read from and who's reading them. Then, of course, we have the cross references API. So it'd be pretty easy, I think, to put together a tree view of our cross references, but then also through time and see and just literally be able to see how data is being passed around the program. This is really promising and, well, useful. So I'd love to see people building on top of this and extending it and what we end up doing with it in the future. No, casually, always thinking of another Tonto slice I can write. I think that would serve well as one. My favorite upcoming features in the next stable. I mean, time travel has been getting a lot of love. That's why we're showing it off today, because people can't seem to get enough of it. And I think there's a lot for us to learn now that there's a nice, easy to use UI in Binja that wraps it. There's a lot of tricks that we could afford to pick up, like what Shishang just showed, being able to be in the middle of a function and not know what it is, and just being able to look at the inputs and outputs of that function to see the values and give you hints towards what it'll become or what the data transformation is that's going on. That's really neat to be able to do. I think that's like that right there just solves a lot of problems. What does the function do? Well, look at its inputs, look at its outputs. Can't be doing too much more beyond that. Um, but you can also query, I guess, are you able to query between timestamps, all the writes between two timestamps?
Yes.
Oh, okay, cool. So then you can to be able to check whether a function and all the functions it calls is interacting with data variables, you could literally just get the before and after timestamps and query for all the writes being made during that. Again, the T stuff, it's just so cool. There's so many different things that it seems like you can do with this.
Yeah. All right. So I am sorry for that. I just can't remember how I did it. I probably just looked over and find so what I was trying to do is basically we're deep inside of the JSON library and I just try to rewind a few call stacks and I remember is that at a particular stack location we basically were just at a you know when we rewind before the core and see what is in the RCX, RDX, and R8 and R9, and after core, one of them will actually hold the buffer we're looking for. But I didn't put it in node. That is pretty bad. So uh, yeah, we can just try any of these and see if that is actually just what we are looking for. I know it's kind of awkward to do it this way, but okay, this is the moment. All right, so nothing happened. We are at this location. Uh,
Cool.
Basically, this is the location where the JSON we're out of the JSON parsing, and we are at the location where we do have a clean buffer of the our so the string. And I already explained what happened is basically I will just trace the JSON parsing and just see what is happening in the stack and get the buffer out of it. Yeah, sorry about that. It's not the way I wanted to do it, but anyways, we're already here, and let's move forward. Okay, so the next thing we are going to do here is we want to see where it goes to. Now, this is still a hex string. We know it has to be parsed before it can be used, right? So we're at 9F013E5, and
How
we
is it
we
that you
want to
keep
see
showing
where.
that? Are you just hitting G to show your current timestamp?
No, is so we are yes, it's Shift G. It's kind of like a
Oh.
enhanced G. Like press G, you go to anywhere, right?
Mm-hmm.
Press Shift G, you go to any time step and also navigate to the current instruction pointer at that location. Sorry, at
Okay.
that time step.
And it's also showing
So
you the current timestamp when you open that?
yes,
Okay,
so you know where you're at.
as opposed to showing that in the bottom right where the addresses are?
Oh yeah, we should totally show it here as well, but I just
Okay,
haven't really added that.
all good.
Just
Just curious.
yeah, yeah. All right, so we are going to navigate to here, and again, we're inside of map copy, and we are just going to repeat the process, let it return, and step over backwards. This basically gives us the buffer that is being copied, and we're just going to care about RCX because that is the receiving buffer, and we'll just do a step over, and we will have the copied buffer, and we'll just repeat the process again. Now, of course, you will see this is a little bit repetitive, and I'm pretty sure this can actually be automated, and you know, it's essentially a 10 tracking just done with hand, which is fine for this case, but in the future we might want to make it more efficient. And we are going to repeat this process a little bit. RCX is going to be copied into, and we just I'm pretty sure these time steps are where these copies happen.
Mm,
Yeah, you can see here 9F1, 3F1
mm-hmm.
is things that happens. Yeah, well, let us just repeat this process a little bit, and let's use this as a code view, and RCX is here, and we're going to step over and test this, and going to do this again, and again, and again, and again, until we are out of it, which is a little bit repetitive, to be honest, but you see here, this is the nice, yeah, you can see here, this is exactly the next time step I have 9F3 ED5. This is slightly different from this because I probably selected a different byte. It's probably I selected this byte when I did it.
That makes sense. It's cool to watch you chase down the blows effectively here,
Yeah,
following it
I
to the
mean,
next copy and the next copy.
yeah.
I think this touches on one of the comments somebody made on the stream of like if there were more copies, what would it look like? And I think this is what it looks like. You just keep following it.
No, I mean, I think yes. So this is a linear, it copies from A to B and copies from B to C and
Hmm.
copies from C to D and eventually somewhere gets used. What would happen if it's copied into A1, A2, and A3 and A1 is copied into B1, B2, B3 and
Mm,
A2 is copied in. Now that would pose a challenge for my manual approach because I would just lost my mind and wouldn't be able to do that. But it wouldn't be a huge problem if you have some sort of the automation, or at least you can control the depth of how it goes, goes into this. copying tree, let's just call it this way. I don't know whether we have a term or something. We can maybe we can control how deep into the recursion we want to get. So
Yeah.
maybe in 3 layers we have 30 destinations, but we're all good because 30 is pretty manageable if you have a table or something. And also modern compilers and CPU architectures or operating systems are written in a way that tends to minimize any memory copies. So I'm not really concerned of some code that comes out of a compiler will just have many, unnecessary copies. But this is a
Right.
could be a different story if somebody tries to target TTD and tries to obfuscate. But again, if we're just dealing with malware, I feel like it should be just fine for now at least. For
Somebody's
now
asking
until the
for a sidekick integration with TTD, so you're gonna have it do it for you.
yeah, for sure. We can totally do that. Yeah, we are into 9F3 something is still inside of mem copy, still getting out of mem copy and rewinding back. And you know what I felt when I initially did this, because I was also not sure this would eventually work. So I was actually at one time even worried about whether I already did like maybe 5 or 6 times of this and this before I get here. So I was even thoughtful about myself whether this is going to be working at all. But yeah, luckily it actually worked. Uh,
Well, yeah, it's interesting. I often tell people that they don't need to read every line of code, and the program is meant to transform data, so you can just follow the data, and you're proving that out right now to any of my students who are watching. Just being able to see that, yeah, no, you don't even really need to understand what the code is doing sometimes at all. If you can just follow where the data is being transformed and being stored to, um, we just need to get out the
yeah.
flag in this case. We just need the result of the calculations.
Yeah, we're at something slightly different right now. So you can see here, I'm plotting an RCX, and after copy, it actually only copies 2 bytes here.
Mm.
This is slightly different. I, I'm not gonna lie, because I see my note, I know what's happening. It's basically this is where it is being parsed as integer, right? So it actually starts a different pattern, which means we're getting out of the memory copy hell from there, and we are getting into somewhere it actually becomes some more, useful thing. So we're going to, again, we're still going to track the read here, but we expect something to be more interesting from now on here, 9F3. Uh, yeah, you can see some of the processes can definitely be improved. Like, we should actually just show where we are in this map so that you don't really have to, do all of these stuff and potentially do it wrongly. But I guess I'm fine with that for now. Okay, okay, all right. So let's not remember. You can always just look up one or two stack frames up when you do TDD while you're tracing, because this is where the string to long happens. That we can step forward a little bit. Uh, it's actually converting 6B to uh, an integer.
Mm.
You can see here. This is the partial string that is being parsed. So it actually converts every hexadecimal string to a actual value. You can see here the
Again,
one
it's
that is
so cool that you can go to the stir to TOL there,
yeah.
and just walk backwards to the string to see which bytes it's actually converting. Just go
Yeah,
back
you
and
can even
forth.
see here all of the places where this call string too long is called, and you can see the numbers actually roughly matches with the string. so that you're pretty sure that is correct. That is actually just parsing everything into a string, sorry, into a integer, and you can see AL does have 6B in it.
Mm-hmm.
Now, so here we actually made progress, right? Because we're coming out of a buffer received on the socket and goes through the JSON parsing and eventually further goes into the integer parsing. And we have the value here, and we can see where it goes into. It goes to here, right? RDX, where it's being put as here. Okay, cool. And I don't remember what happens next. So this is a loop, right? You see here is a loop. And I guess the loop is just looping through the string and parsing everything. And at the end of the day, we should actually just have a string, an integer that is parsed, right? Let me try to see how many times this is actually get executed. So this is another thing that you can't really
You
do
just cut out for a
in
second.
oh sorry. So
And you're back now. You cut out
yeah,
for a
okay,
second
cool.
there.
All right. So, do you guys hear me now?
Yeah.
Sorry about the cutting off. Okay. So this is also another thing that I find really cool, and you also cannot really do easily in regular debugging. Is basically you have a loop, and you have a sense of maybe it runs for 100 or 200 times, and you can actually see all of the times that it executes, and see whether that number matches your expectation, right? So this is the integer parsing loop, and I kind of like expected to the number of its execution is roughly the same as the byte string length.
Oh,
And
wow. Yeah, okay,
yeah,
interesting.
137 is definitely something that is correct, right? So that just gives me confidence in moving forward on this before, like I have to take a step back and see whether I'm doing the things correctly or, stuff like that, right? So
Do you have any other features that allow you to see just how many times a loop got executed, or is it just
no,
through this
I
write?
just select this instruction as and ask it to give me all of the time
Oh,
it has been
okay.
executed.
Yeah.
Yeah. Now it's not really always accurate because the loop can be executed at different times and
Yeah.
maybe but these time steps are pretty clear, pretty close, sorry. 9F3 small increments, right? So you just
Hmm.
have a feeling that is correct. Now,
Yeah, that makes sense.
again, admittedly, this is not really this is not really scientific, right? You could be wrong or stuff like that.
It's all just signals contributing to our confidence about things.
Yeah, I think what you said is making a lot of sense to me as well. It's basically you don't have to really understand all of the code. Like this function is I don't know what it's doing. It's probably some library code, and I have no interest in understanding them. But I know it's parsing integer, so I just want to get the integer out of it and see where it goes to.
Right.
And yeah,
Well, if we wanted to
let me see
brute
what.
for right now, you're going and trying to find the instruction that's writing out the results, I imagine.
Yeah.
So the other
So this
brute
is
force way to do this would be to maybe try to find all writes by this region of code, made by this region of code. But there's probably tons and tons of writes being made by all this code.
so I'm kind of confused because after the string too long, I remember it just gets written to a buffer, which is the integer. So I am not sure what's happening. I guess written to here. DX. And then increments the counter. That's weird. Yeah, let me see what's happening here a little bit.
If you looked at one of the ILs for a second, would it be more obvious?
Could be. String to one is parsed to. Oh, so it's. Oh, I see what's happening. So is convert. This is the typical like string appending behavior. It's like what if the lenses are still good, it's still if the lens is no longer good, it has to reallocate, right? The operator new stuff. Otherwise, it just write the buffer to it.
Ninja, this is all,
And
we
this,
have APIs wrapping all this stuff. So you don't have to use Microsoft's API. You can use the nice, clean Binja API that you've come to know and love to get all this information out.
yes. So answering to that, we not only have the UI, we also have the the whatever the API for that in Python. So Microsoft also actually exposes a JavaScript API for that, but I am not a fan of JavaScript, so I just excuse myself for not being good
No,
at
my
it.
favorite feature of 5.2 that's coming out is the binary ninja JavaScript bindings.
Oh yeah, we should definitely have that. All right, so
Ninja
I am
compiled for WASM is a thing that might happen eventually, I can imagine.
yep. I'm just going to cheat a little bit again. I somehow find these time steps when I was not under pressure.
Yeah, we
I don't
get
know.
it. By looking at the memory reads and
Oh,
writes, you find where
okay.
things are being
I
passed around.
This is what I did. I just stepped a call frame back up, and it just and then it just
Right.
I just see what happened after that. Yeah, this is actually the parse integer function.
Okay,
Yeah.
cool.
Yeah, I think the reason why I know this is because we were actually inside of this function earlier. You still remember, right? We were at this function. What I did is basically I just rewinded one stack frame up,
Hmm.
and I see what is in RCX, and I just execute it, and it probably just has the integer in it, and I see, okay, I see what this function is doing. Oh yeah, you can see here, this is the buffer parsed into a integer. It's
Okay.
no longer showing string 085D. It's showing you know, the actual integer. So this is actually how I figured it out. It's just uh, you can go to the caller and see what is the parameter, and then just step over the call and see how it changes. RDX of course doesn't change, so RCX does change, and it does actually has the integer, right? So this is actually the parse integer function, and we found
Hmm.
it. We found it the integer in a buffer, and then we're just
Interesting.
going to repeat the process. Yeah.
I was
Uh,
expecting us to get a string out of that. I wasn't expecting it to be just random bytes. Is this
no, it
shellcode?
will be. No, this is an integer. This is data. This is data that has to be decrypted. So
Oh,
the
okay.
next thing that happens is decryption. So we are at 9F8. So the next time it reads is 807. Yeah. Again, I mean, I admittedly this process is not as smooth as I would prefer in a, let's see if it's a edited video or something, but this is just how, roughly speaking, how I actually did it, right?
No, this is awesome. So
So
we were able to find the data come over the network. We were able to follow
yeah,
some copies within Binja. Then we were able to find the JSON parsing, where it's parsing hex integers to real integers. And now we found the final result buffer of that integer calculation, which is about to be passed off to some more parsing. So we're going to find that
yeah,
now, right?
yeah. So somebody asked about TTD coverage. It's basically it can coverage all of the instructions for that has been executed. It also works for this, but I don't want to try it because the indexing can take a while and can
Mm.
potentially cause issues. But
Th-
basically, you
This
just open TTD
window
analysis.
This one is really
You showed
interesting
it.
to me. What else are you planning to add to this? What are other analysis types?
We do have a call tree plan. So now we have a call stack, but the call stack is just like a small slice of a call stack, right?
Yeah.
Sorry, call stack is like a slice of the call tree. You don't see the siblings. You see the parent and son. You don't see the siblings. But in a call tree, you see actually the siblings of a function call. It's basically of one function maybe calls another five functions, and we can see this relationship. That is something I plan to work on. And also, the string scanning I mentioned
Oh, right.
earlier is also something I'm trying to build.
That
And
makes sense.
also, yeah. All right, so I'm getting excited because I already recognize this code. This code is having a totally different pattern than the thing we showed earlier. It's actually iterating over the string and does some processing. So you can see here REX is pointing to this buffer and RBX is having a value of 10. And this is actually the place where this buffer gets processed. Now I'm going to copy this time step into somewhere else in case we lose it because I don't want to lose it. And for now, I'm going to switch to a high-level IL because I remember the code from here is more readable if we go to the high-level IL. Okay, cool. Go to the RIP. Can see here. We still have the buffer here so that we remember what is its value. And also can see here, we are at here. Okay, here, let me show it in this. Okay. So we are, where is it? Oh, okay. So what we're doing here is basically arg2 is the string, and we're taking the ith of the string and doing a sbox lookup.
Hmm.
Uh, yeah, you wouldn't really see this as sbox immediately. Of course, I just remembered it from seeing this, but this is actually just a sbox lookup. And after that, you get the value R10 underscore 7. Now we're looking at obfuscated code, right? Remember that? And also we haven't really doing a deobfuscation of that, but it doesn't matter because we have cross references to variables. We have R107. Okay. So
Yeah.
we're at
It
this
doesn't matter
instruction
that the
where
code is
R107
obfuscated
is
as the
assigned,
data
right?
flow is not.
And oh, we're having the next place where that is being updated. R107 is being updated by adding hexff minus I and then XOR with I mod with RDI. So basically this is where this byte gets decrypted, right? You can see where it goes to is uh, we first read it from the buffer and then do a lookup and then we do a decryption. I remember this decryption is then put into a not sure where it is. Yeah, this is where it gets the char gets processed, and this is where I remember is this function is std colon colon string append or something. So basically, R10 is a decrypted char, and it gets to be uh, uh, you know decrypted. So uh, yeah, I okay, cool. Let me just show you guys the eventually decrypted string. Can you see here? We can see this. Again, now we are seeing all of the times where this particular place is, let me give it a better name. So the decrypted chart is appended into RCX, which is, I believe, yeah, we can pretty much just look at where this string. I
If you
think we can
find it,
just navigate to maybe the last time this happens
yeah.
and see what we have in the string, because RCX is actually the string, right? And we can see it. Yeah, this is the decrypted string of the buffer. Now,
Okay.
this still remains unreadable because I am sending a invalid response. So this is actually what I
Uh,
sent to the client. If I were to send a thing that is actually accepted by the client, it will look something like this. Uh, server to the client. Yeah. So I remember this is what is a valid um, response after decryption should look like. It looks different from my garbage, but uh, this is basically how I trace the decryption. So we trace the decryption from the buffer after it is received, and then uh, out of the JSON, and eventually into a decryption routine. And we can see here this is where it's getting decrypted and uh, further uh, used by the uh, target. Now, so the thing I did next is now that I know how this is decrypted, so I can actually use the algorithm to decrypt the actual thing that is captured in the packet capture, right? And that can be decrypted to something reasonable. And then I can continue the communication with the client because I know how this encryption is done. Um,
oh, I see.
yeah,
Because
I think we're pretty deep into this, and given the challenge, the complexity of the challenge, I feel like I already demonstrated how TDD can be helpful for this. So Kyle, do you think we just maybe wrap it up here, or you
yeah, I
guys
think
want
we
to
can.
see a little bit more of how to do the thing?
Can you just show where that decryption logic lives? Because you have
Hello?
that function you've remade in Python here, but where did we see that in the binary? Oh, can you not hear me right now? No, you're all good. Oh, stay. You guys can hear me, but Shushan can't at the moment. Hey, can you hear me again? Try this. Can you hear me? All right. It's all good. Um, Maybe his headphones are off. But yeah, no, I think that let's switch to my camera here. I think that we demonstrated how you can use the time travel debugging features to bounce between um, a bunch of different data and be able to find where values are being passed around and how they're being modified and all stuff like that. If Shushan can come back, or Shushan can hear me again, it would be cool to see where that actual decryption logic was. But I think he showed us that XOR, and you guys can skip back to see where it was happening as well. So, unless there are any other questions for Shushan, thank you guys for sticking around. It's been another great stream. Come back next week at 4 p.m. Eastern Time. We'll be interviewing one of our Reverse trainers, Marion. We're going to have a quick interview, going to ask her some tricky questions, and then she's going to show off possibly some cool visualizations she's been working on, or possibly something to do with her class. So if you've been thinking about taking a class at Reverse, not sure which one you want to take, we'll have a couple people. We have Marion, we have Tim, who are both going to be on stream, and you get a little taste of how they're like. In addition to me, you'll be seeing me on stream every other week. And if you want to take my class at Reverse, I'd love to see you there. But thank you guys for sticking around, and we'll see you again. We'll see you again next week. Have a good one, everyone.